The nuclear binding energy is the amount of energy required to break down a nucleus into its constituent parts, protons and neutrons. But to get an understanding for this, we're going to have a look at it from the opposite direction, the change in energy associated with those parts being forged into a nucleus. The first thing we're going to have a look at is the masses of these separate entities. In this example, 8 neutrons and 8 protons coming together to form oxygen-16. The mass of a neutron is 1.67804 times 10 to the minus 23rd. A proton, slightly less, 1.67262 times 10 to the minus 23rd. And oxygen-16, 2.65535 times 10 to the minus 23rd. Now we'll have a look at the masses added up. Here, the mass of 8 neutrons and 8 protons is 2.67804 times 10 to the minus 23rd. If we're to think beforehand, before we knew about Albert Einstein's equations and things like that, we would think that these masses should be the same. If I took 8 individual neutrons and 8 individual protons and added them up, it should be the same as this oxygen, which is 8 protons and 8 neutrons. What we're going to find out is that it is not. We'll take the oxygen mass, 2.65535, minus the combined masses of 8 protons and 8 neutrons, which is 2.67. Already we can see that this number is larger. And the result is negative 2.269 times 10 to the minus 25, which means that when 8 protons and 8 neutrons form an oxygen nucleus, it actually loses mass. We'll have a look at why. First, what I did was converted this to grams per mole, so multiplied this by Avogadro's number, so it's minus 1.366 grams per mole. So for a gram of oxygen that is formed from protons and neutrons, every mole of oxygen that is formed, it is a loss of 0.1366 grams for every mole of oxygen that is formed. This is how much mass that is lost. Now, to understand why it has less mass, we need to look at Albert Einstein's relativity, where it says that energy is equal to mass times the speed of light. So a change in energy means a change in mass, because the speed of light is constant. The speed of light cannot change. So if there's a change in energy, there's a change in mass. So why worry about this now and not worry about it in chemical reactions earlier? Because there's a change in energy there. And the reason we don't care about it in those earlier chemical reactions is because the change in energy is so small comparatively that it's completely undetectable. And we'll have a look at why. So look at the change in energy for this. We'll take minus 0.1366 grams per mole and multiply it by the speed of light, and this will be the change in energy. And this is equal to minus 1.23 times 10 to the 13th joules per mole. So already right there, that is a number much, much larger than anything we have ever seen in a chemical reaction before. Even the most exothermic reaction is not even close to this. So the reason that we don't care about the change in masses and other chemical equations, it's not because there is no change in mass. There is, but it's so small that it's not even worth noticing. So from here, back to the idea of nuclear binding energy. This is the amount of energy that is released. per mole of oxygen formed from these constituent parts. Now what we do is we convert it back to a nuclei, because this nuclear chemistry, we don't really care about moles so much, because normally with the quantities of things that are dealt with on this nuclear physics level, particle physics, it's always in very small quantities. We're always looking at things from the perspective of a single nucleus or atom mostly. So the units, the rest of this is really just a conversion to units that are used more frequently in this field of study. So we're going to basically convert joules per mole to electron volts, million electron volts. So we'll take these joules per mole, convert it to nuclei again, so we'll get rid of moles cancel, and this is minus 2.04 times 10 to the minus 11th joules per nucleus. Now we'll use this MeV, which is in electron volts. So now we'll make the conversion, minus 2.04 times 10 to the minus 11th joules per nucleus, and convert to MeV. This is equal to minus 7.98 MeV per nucleus. And this is the energy change associated with the formation. Nuclear binding energy is concerned with breaking it apart. So all we really need to do is just flip this equation around, and we'll have nuclear binding energy. So this will change from a negative to a positive, and that is what this is right here. It's basically what we just looked at, but going in the opposite direction. Instead of the energy change associated with the formation, this is the amount of energy that's required to break apart a single nucleus of oxygen into its constituent parts, 8 neutrons and 8 protons.